let's look at a few more ways of, let's look at a few problems to solve with power series. This is a solution about what we call ordinary points. We're going to consider the differential equation a sub 2, which is a function of x, y double prime, plus a sub 1, which is a function of x times y prime, plus a sub 0, function of x times y equals 0. If we go ahead and get it into standard form, or divide through by the a2, we get y double prime plus p of x y prime plus q of x y equals 0. X0 is called an ordinary point if p of x and q of x are analytic. Remember, analytic means they can be written as power series. So think of it as long as they're basically, in a way we think of them as being continuous. If they're not ordinary points, we call them singular points. Things get a little different around singular points. And there's a whole bunch of discussion of what you can do with singular points. We're going to actually look at just the ordinary point ones in this section, but there are singular points you can talk about and what happens around those singular points. This theorem says if x equals x0 is an ordinary point of this differential equation, a2 x y double prime a1 of x y prime plus a0 of x times y equals 0, then there are two linearly independent solutions of the form y equals a summation n equals 0 to infinity of cn x minus x0 to the n, which converges on some interval x minus x0 is less than r, where r is the distance from the closest singular point to x0. So let's actually do that. Let's go ahead and find out what the lowest bounds are for r. If we have a different equation, x squared minus 2x plus 10 times y double prime plus x times y prime minus 4y equals 0 for x sub 0 equal to 1. So we want to actually find out what that lower bound is for that r. So the very first thing we're going to do is we're thinking of, with these, we divide through by that p of that a2 sub x. So these p of x and q of x need to be continuous. So we need to find out where are these continuous. So we need to know where x2 minus 2x plus 10 equals 0. So we've got x squared minus 2x plus 10 equal to 0. That actually equals 0 when x is equal to 1 plus or minus 3i. And you're like, oh, great, we're complex numbers, everything's fine. But that's not exactly true. R is the distance from that 0, 0 to this point. You haven't probably spent much time with complex numbers, but it is in the complex point plane, we can actually talk about that distance. This is actually in the complex plane. This is the point. If this is your real part and the vertical axis is your imaginary, then we're going to go up 3 in the imaginary and over 1 in the real, and we get a point. So this is actually the point 1 plus 3i. We can also do 1 minus 3i. And we're looking at how far is that from closest point to that singular point. We're looking for that distance. And so we're looking for how close are we to 0. So we're looking for this distance here from that point to 0. Well, that's just that's r. That's what r is. So it's from the point 1, 3 to the point 0, 0. Well, that's just a line. That's just a line you're looking at. So you're just looking for the length of that line. And the length of that line would be the square root of 3 minus 0 squared plus 1 minus 0 squared. The distance formula. So it's the square root of 9 plus 1 or the square root of 10. So that's what your r is equal to 10, the square root of 10. If you're looking at being from the point x equals 0, so this was x0. If we did from the point x equals 1, so this is when we're saying x equals 0. and that point is from that distance. If we're looking at how far we are from x equals 1, then r would equal the square root of 1 minus 1 squared plus 3 minus 0 squared. Because again, in x equals 1, the real part is 1, the imaginary part is 0. So that would be all of the square root of 1 minus 1, of course, is 0, and square root of 3 squared is 3. So we have. So it depends on what point you're working on and what your initial point is you're looking into. Okay. We actually want to find two power series solutions about x equals 0 for this differential equation y double prime plus x squared y equals 0. And so we're going to look at how we do this. Again, we know that these are going to be of the form y is going to equal the summation n equals 0 to infinity of Cn x to the n. So first, if we know it's a solution, we can plug it in. So we can go ahead and plug this into here. But to plug it in, we need to know what y prime and y double prime is. So again, you're going to bring the power down, subtract 1 from the power. So you're going to get n Cn x to the n minus 1. But instead of starting at n equals 0, again, when you take a derivative, that first term would go away. So this one actually starts at n equal 1. Y double prime, again, bring the power down. So you get n times n minus 1, c sub n x to the n minus 2. But now, same idea, is you won't start at n equals 1 this time. You're going to start at n equals 2. So every time you take a derivative, your index increases by 1. All right. So now that we've done that, we can plug these in. So we have the summation n equals 2 to infinity of n times n minus 1 c sub n x to the n minus 2 plus x squared summation n equals 0 to infinity of Cn x to the n equals 0. Okay, all is good. This is great. So now what we have to do is we again want to have these both have x to the n. So we're going to do some work to get these both to x to the n. But one thing I want to point out is this one has an x squared in front of it. We can bring it inside the summation because it doesn't involve n. It can come inside the summation. So we end up with n equals 2 to infinity of n times n minus 1 c sub n x to the n minus 2 plus the summation n equals 0 to infinity of Cn x to the n plus 2. When you bring it inside, you just add them. Well, great, except now we need to shift things because we both want these to be x to the n, and they're not. One is x to the n minus 2, one is x to the n plus 2. So for both of these, we need to do figure out what my new n is going to be. In this case, we're going to let n equal n plus 2, because n plus 2 minus 2 will give me n. This one over here, we're going to let n equal n minus 2, because n minus 2 plus 2 is, of course, n. All right, so that's what we're going to put into these. So we're going to the summation n plus 2 equals 2 to infinity. N plus 2 minus 1, c sub n plus 2, x to the n plus 2 minus 2, plus the summation n minus 2 equals 0 to infinity, c sub n minus 2, x to the n minus 2 plus 2 equals 0. So I'm just shifting all of my indices. I'm shifting my x's. I now happen to have the summation n plus 2 equals 2 means n starts at 0 if you get n by itself. N plus 2, n plus 1, c sub n plus 2, x to the n, plus the summation n equals 2 to infinity, c sub n minus 2, x to the n equals 0. So we now have everything in the right format. We want to put these together into one summation because we both have x to the n in both of them. But this one starts at n equals 0, and this one starts at n equals 2. So I can actually get this one from n equals 0 to n equals 2 by just writing out the first few terms. If n equals 0, we're going to have 0 plus 2. times 0 plus 1 times c to the 0 plus 2, so c sub 2. X to the 0 means there's no x. Plus, if n equals 1, then we're going to have 1 plus 2 is 3. 1 plus 1 is 2. C sub 1 plus 2 is 3. X to the 1. Now it's going to start at n equals 2. So we're going to have n equals 2 to infinity of n plus 2, n plus 1, c sub n plus 2. Now if they're going to have these both are the same indices, they're both starting at n equals 2. We can actually put them together. C sub n minus 2, factor out the x to the n, and then the whole thing equals 0. All right. So now what we're going to do is to look at this is we're going to realize that just as we did before, if these terms equal 0, if everything equals 0, then that means that this first term has to equal 0, because this is the only term that has no x's in it. So 2 sub c2, 2 times c2 has to equal 0. Well, the only way that can equal 0 is if c2 equals 0. Okay, because otherwise it can't equal 0. The other one is 3 times 2 times c3 is the only coefficient of x to the first power. So that has to equal 0. So that tells me that c3 also has to equal 0. The rest of this says to me that n plus 2 times n plus 1 times c sub n plus 2 plus c sub n minus 2 is all the coefficients of every other extra power, and they all have to equal 0 because x can never be 0, because otherwise it'd be really boring. Here, though, my n doesn't start at 0, my n starts at 2, because this is where my summation starts. So n equals 2, 3, and so forth. Great, so at this point, what I'm going to do is I'm going to go ahead and start substituting in my different n's to see if I can see a pattern and see if we can come up with a pattern to these and find out what we get. So again, my n is starting at 2 and so forth. So let's let n start at 2. That will get me, oh, let's go ahead and get, I'm sorry, I shouldn't do that just yet. Let's get our c sub n by itself. So let's actually get the c sub n plus 2 by itself, because this is c sub n minus 2, and we're starting n at 2. So we're going to get this term by itself. So c sub n plus 2 is going to equal minus c sub n minus 2 over top of n plus 2 times n plus 1. And again, n starts at 2 and 3 and so forth. So if n equals 2, that would be c sub 2 plus 1. 2 is 4. It's going to be minus c sub 2 minus 2, which is 0. 2 plus 2 is, of course, 4. 2 plus 1 is, of course, 3. So we get that. N equals 3 gives me c sub 5. That's going to be minus c sub 3 minus 2 is 1. Over top of 3 plus 2 is 5. 3 plus 1 is 4, so 5 times 4. Okay. If I know c sub 0, I can find c sub 4. If I know c sub 1, I can find c sub 5. I don't know them, but if I knew them, I could find those. Let's look at, and you can find this, by the way, if you have an initial value problem. So if you had an initial value problem, you could actually find out what those are, but we don't have an initial value problem. Let's let n equal 4. That would be c sub 6. That would be minus c sub 4 minus 2 is 2. 4 plus 2 is 6. 4 plus 1 is 5. So if I know what c sub 2 is, I can find out what c sub 6 is. But I do know what c sub 2 is. C sub 2, we found out, was 0. So I actually know that this one is 0. So c sub 6 is also going to be 0. Let's do n sub equals 5. That'd be c sub 7. That'd be minus c sub 3. 5 plus 2 is 7. 5 plus 1 is 6, so you have 7 plus times 6. So again, if I know what c sub 3 is, I can find c sub 7. But I do know what c sub 3 is. We just found out c sub 3 was also 0. So that tells me that this one's also equal to 0. Let's keep going. We don't really see much going on here. Let's try a couple more. Let's try n sub 6, n equals 6. So that would be c sub 8. That'd be minus c sub 4. My 4 look like a 4. That'd be 8 times 7. So if I know c sub 4, I can find c sub 8. But I do know c sub 4. It's minus c0 over 4 times 3. So this is going to be minus a negative c0. So it's going to be positive c0. 8 times 7 times 4 times 3. If n equals 7, that would give me c sub 9. That would be minus c sub 5 over 9 times 8. So again, if I know c sub 5, I can find c sub 9. But I do know c sub 5. It's minus c1 over 5 times 4. So minus a minus is going to give me c1. 9 times 8 times 5 times 4. Great. Let's try just a few more. It always helps to do a lot of these just to see what's going on. N equals 8. That'd be c sub 10. That would be minus c sub 6 over 10 times 9. Again, if I know c sub 6, I can find c sub 10. But I do know c sub 6. It's 0. So this is 0. N equals 9. That'd be c sub 11. That'd be minus c sub 7 over 11 times 10. So if I know c sub 7, I can find this. But I do know c sub 7. It's also 0. So let me fix this messiness here. So that one also is 0. So I can see that any of the ones that don't have a C0 or C1 will become 0. Let's just do one more just to make sure. N equals 10. That'd be C sub 12. That'd be minus C sub 8 over 12 times 11. Again, if I know C sub 8, I can find C sub 12. But I do know C sub 8. It's C0 over 8 times 7 times 4 times 3. So this is going to become equal minus C0, 12 times 11 times 8 times 7 times 4 times 3. I'm not seeing a great pattern happening here. And if you're really good at these, you could probably come up with some weird pattern, but I'm not really seeing a good pattern here. So at this point, I'd probably just go ahead and multiply these together. 12 times 11 times 8 times 7 times 4 times 3 is actually equal to 1440. And that should be C1, sorry. No, it is C0, sorry. Okay. This C1, 9 times 8 times 5 times 4, that would actually be, actually, that's the 1440. So I actually didn't find out what this one is. We don't care really what it is. So we'll just go ahead and delete it for right now. If you want to know what it is, you can find it. C sub 8 is C0 over 8 times 7 times 4 times 3. So 8 times 7 times 4 times 3 is 672. We have 0 and 0. And then, of course, we have minus C1. 5 times 4 is 20. And minus C0 over 12. So now we can go ahead and write out what y is. Y is going to equal C0 plus C1x plus C2x squared plus 3C3x to the cubed plus C sub 4x to the fourth plus keep going on for this pattern forever and ever and ever. C0, we don't know what it is. C1, we don't know what it is. So C0 plus C1x. C2, we found out was 0, so that's gone. That term's gone because it's just 0. C3, we found out, I'm sorry. Yeah, C3 we know is 0, so that term's gone. C4 we know is negative 1/12. C0, so we have negative 1/12, C0 x to the fourth. C5 we found out was negative 1/20. C1 x to the fifth. The next term would be C6 x to the sixth, but C6 is 0, so that term's gone. Plus C7 x to the seventh, but C7 is 0, so that term's gone again. Then we'd have C8. C8 we found out was once positive 1/672 times C0, so that's x to the times x to the 8. Plus the next one was C9, and C9 we found out was 1/1440. C1 x to the 9. And then we just keep doing this pattern. And again, we don't know what the pattern is, we're just writing out the terms. We did want to have two solutions, and we can kind of see we have that. Some of these terms have a C0 in them. Some of these terms have a C1 in them. So Y1 would be the terms that have C0 in them. We're going to go ahead and write them out, and then we can kind of show you what they are. We're going to put the C1 terms together, the C0 terms together. So we have C0 times, we're going to pull that C0 out of those. We're going to have a 1. We're going to have a minus 1/12 x to the fourth. We're going to have a plus 1/672 x to the eighth minus, and it's going to keep alternating pluses and minuses, plus C1 times x. The next term has a minus 1/20 x to the fifth. The next term has a 1/1440 x to the ninth. Again, it's going to be alternating, so the next one's going to be minus. And so the ones that are multiplied by C0, that is your Y1. And the one multiplied by C1, that's your Y2. So there's your two solutions, if you want to know what they are. Let's try one more. Let's solve y double prime minus x times y prime plus 2y equals 0. So again, and you can do these, by the way, with higher order ones. They don't always have to be just second order. Same kind of process works here. We're going to go ahead and say that y in general y is going to equal the summation n equals 0 to infinity of Cn x to the n. We need to know what y prime and y double prime are. These aren't going to change. They're always going to be the same. So y prime is n equals 1 to infinity of n times Cn x to the n minus 1. And y double prime is going to be the summation n equals 2 to infinity n minus 1 c sub n times x to the n minus 2. And again, that won't change. Those are always going to be what your derivatives are. So we're going to put in the y prime. That's going to be n times n minus 1 c sub n x to the n minus 2. Then we're going to have plus or minus x times the summation n equals 1 to infinity of n c sub n x to the n minus 1. And then plus 2 times y. And y was the summation n equals 0 to infinity of Cn x to the n. And that equals 0. And the same process is going to be working. We want these all to be x to the n. First, what we need to do is pull in anything. I forgot my summation on the very first one. I apologize. So put that summation in. That was a summation n equals 2 to infinity. And so I want this x to be x to the n. So that means I'm going to put an n plus 2 in to make this n. I want this one to be x to the n, but I notice there's an x out here. So before you do anything, pull that x inside before you do any kind of work. So we have n equals 2 to infinity. I know what to put in, but we're going to just do it in steps. I'm going to pull that x inside. So it's going to be n c sub n x to the n. I'm going to go ahead and pull that 2 inside just because we don't want to lose it. And so it'd be 2 c sub n x to the n equals 0. So in this case, when we go to do shifting, both of these last two terms have an x to the n already in them. It's just this middle term, this first term, sorry, that doesn't have that. So we're going to put in an n plus 2, and everywhere we see an n in this very first one. So n plus 2 equals 2 to infinity. N plus 2. N plus 2 minus 1 is going to be n plus 1. C sub n plus 2. X to the n plus 2 minus 2, which is x to the n. The rest of these are already with an x to the n, so we're fine. The other thing is I'm going to go ahead and just erase this. I know that this one's going to start at n equals 0 because I'm going to have n plus 2 equals 2. So that's going to be n equals 0, just so we know what the summations are starting. Again, I want to put these all together. I notice I have 2 summations that start at 0. I have 1 summation that starts at 1. I need them all to start at the same place. It's easiest to make them go to 1. So we're going to start this first one. We're going to go ahead and write in n equals 0. So if n equals 0, we're going to have 2 times 1 times c sub 2, x to the 0, which means it's not there. Then the other place was this last one, starts at x equals 0, so it's going to be plus 2 times c sub 0. X to the 0, of course, is just 1. Now they're all going to start at n equals 1. So now we're going to go n equals 1 to infinity. We're going to have n plus 2 times n plus 1 times c sub n plus 2. That's going to be times x to the n. Minus n times c sub n. We're going to factor the x to the n's out. Plus 2 c sub n. Factor the x to the n's out. Equals 0. So again, the terms that do not have x's in them have to equal 0. Because the coefficient of on the other side is also 0. So we have 2 times C2 plus 2 times C0 equals 0. We also happen to have that all the coefficients of x to a power has to equal 0 because there are no x to a power on the other side. So we have n plus 2 times n plus 1 times c sub n plus 2. Notice I did not multiply those out. I don't want to multiply them out. I'm looking for patterns. So you try not to multiply things out when you're looking for patterns. Minus n times c sub n plus 2 c sub n, and that has to equal 0. Normally we start with the higher order one. So the higher c sub n, in this case c sub 2 is the higher one here. So we're going to get c sub 2 by itself. So c sub 2 is equal to negative c sub 0. So if I know c sub 0, I can give you what c sub 2 is. And then the other one, I'm going to solve for c sub n plus 2 because it's the highest index. So c sub n plus 2 is going to equal n times c sub n minus 2 times c sub n over top of n plus 2 times n plus 1. I could actually notice that I could pull the C sub n out. So this is actually n minus 2 times C sub n. If you want to do that, that's probably not a bad idea. It makes life a little bit easier for looking for patterns and not doing so much. So we're going to go ahead and factor out that C sub n. So we have an n minus 2 times C sub n over n plus 2 times n plus 1. Okay. In this case, my n starts at 1. So my n is starting at 1 and going on up. So n equals 1 is where we're starting. N equals 1 means we're going to have C sub 3. We already know what C sub 0 and C sub 2 are. Well, we don't. We know what C sub 2 is in terms of C sub 0. If I give you a C sub 0, I can find C sub 2. C sub 3 would be 1 minus 2 is negative 1. C sub 1 over top of 1 plus 2 is 3 times 2. Again, I'm not going to multiply anything out. I'm looking for patterns here if I can. All right. So now let's go n equals 2. So that'd be C sub 4. That would be 2 minus 2 is 0. So that's 0 times C sub 2 over top of 2 plus 2 is 4 times 3. I didn't really need this one because I know it's 0, but I went ahead and did it just for the sake of having it. Let's try a couple more. Let's try n equals 3. That would be C sub 5. That would be 5 minus 2, which is 3. No, it's not. I'm sorry. I apologize. N is 3. So it's going to be 3 minus 2 is 1 times C sub 3. And then it's going to be 3 plus 2 is 5 times 3 plus 1 is 4. So 5 times 4. So again, if I happen to know what C3 is, I can find C5, but I do know what C3 is. It's equal to negative 1 times C1 over 5 times 4 times 3 times 2. Cool? All right, let's keep going. Let's do a couple more. Let's do n equals 4. So C sub 6, that would be C sub 4. C sub 4, sorry about that. And so then we notice it's going to be 6 times 5. C sub 4, we had it 0. So we know this one's 0. Let's do n equals 5. That would be C sub 7. That would be C sub 5 over top of 7 times 6. So we know what C sub 5 is. We can find C sub 7, but we do know what C sub 5 is. It's negative C sub 1 over 5 times 4 times 3 times 2. So we have 7 times 6 times 5 times 4 times 3 times 2. We can keep this going if we wanted to. And then you can also realize that I made a mistake because I forgot that I have an n minus 2 in the top. So let's go back down here. We have an n minus 2. 3 minus 2 is 1. So that's why there's a 1 here. So I'm going to put a 1 here just to remind myself of that fact. It's a good idea to do that so you don't just make them go away. Then 4 minus 2 is 2. So we have a 2 in the top there. And then 5 minus 2 is 3. So we have a 3 in the top here. Okay. So now if we can see if we can have some kind of pattern, if we want to try to come up with some kind of pattern here. I notice in the bottom here is 3 times 2. Well, 3 times 2 times 1 is 3 factorial. So this means I actually have negative 1 times C1 times 3 over 3 factorial. In this one, I notice in this one, I have negative 1 C1. I have 5 times 4 times 3 times 2. Again, that's just 5 factorial. So I have negative 1 C1 over 5 factorial. I notice here I have negative 3. It looks like I have 7 factorial on the bottom. So I have negative 3 times C1 over 7 factorial. Again, what I like to do is I like to go ahead and write out a few terms, see kind of what's happening here. Whoops. Let's do something different. So we have now that y is equal to C0 times x to the 0 plus C1 times x to the 1 plus C2 times x squared plus C3 times x cubed plus C4 times x to the 4th plus dot, 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 forever and ever and ever. And so all we have to do is start putting in what these terms are. C0, we don't know what that is, so we're just going to start there with C0. C1, we also don't know what that is, so C1 times x. C2, we actually found out was negative C0. So we have negative C0, x squared. C3, we just found out was negative 1 over 5 factorial. Sorry, not negative 1. Negative 1 over, I'm going to go back and look what I had. I always forget one page to the next. So that was C sub 3 is negative 1 over times C1 over 3 factorial. Negative 1 over 3 C1 over sorry, I always seem to already forget what I wrote. So C sub 3 was negative 1 over 3 factorial. Not 3. That will be x cubed. X C sub 4, we found out was 0. So that'd be 0 times x to the 4th. C sub 5, we found out was negative 1 over 5 factorial. C sub 1, x to the 5th. C sub 6, we found out was 0. So plus 0 times x to the 6th. C sub 7, we found is negative 3 over 7 factorial. C sub 1, x to the 7th, and so forth from here on out. So plus, plus, plus. Putting together the terms we have, we notice we happen to have a C0 all by itself. We notice we have a C1 and a bunch of other terms. Oh, wait, we have two C0s. We have a C0 and another C0. So we pull that C0 out. We have 1 minus x squared times C0, and no other terms had a C0 in them. The next one, however, all the rest of them have a C1. So we have an x times C1, a minus 1 over 3 factorial x cubed times C1, a minus 1 over 5 factorial x to the 5th, and then, and so forth. And then minus 3 over 7 factorial x to the 7th, all times C1. This first one is your Y1. Your second one is your Y2. Your Y1 is just a polynomial. Your Y2 is an infinite series. And that's all there is to finding power series. I would continue to do this where you just keep finding terms. If you want to try to find a pattern, you can. Otherwise, just keep writing down the terms and write as many as you can.